finite difference methods to approximate derivatives numerically. This approximation derives from the Taylor series expansion, which help us to express a function in terms of its derivatives at a specific point. We have three finite difference approximation for the derivative of a function of velocity with respect to x. First, forward difference. Derived from the Taylor series, this method estimates the derivative at a point ij by looking one step forward. The partial derivative of velocity with respect to x at the point ij approximately equal to a velocity at I plus 1 j minus of velocity at ij divided by change of x plus a first order of accuracy or approximation, meaning that the error decreases linearly as the step size change of x shrink. Second, backward difference. Also derived from the Taylor series, this method looks one step backward. The partial derivative of velocity with respect to x at the point ij approximately equal to velocity at ij minus velocity I minus j divided by change of x plus the first order accuracy. Central difference. Using a Taylor series, this method averages forward and backward difference. The partial derivative of velocity with respect to x at the point ij approximately equal to velocity at I plus 1j minus velocity at I minus 1j divided by 2 times of j plus the second order approximation or accuracy, meaning that error decrease quadratically providing greater accuracy. By utilizing the Taylor series expansion, these finite difference techniques transform continuous problem into discrete form, making them solvable on computer. Let's move into the basics of finite difference methods, which are essentially for solving differential equations numerically. Essentially, we replace all the partial derivatives in the equation with what's known as the finite difference quotient. This transformation gives us algebraic equation called difference equation. Take, for instance, the unsteady one-dimensional conduction equation, which involve partial derivatives with respect to both time and space. By using finite difference method, we can approximate this derivative and solve the equation numerically. In this context, we often deal with what's called the parabolic partial differential equation. Here, the solution progress over the time indicates as a marching solution with respect to time. The index I runs along the spatial x direction and n run along the t direction. To solve this equation, we replace the time derivative with a finite difference approximation, enabling us to compute the evolution of temperature over the time using computational method. This approach is crucial for simulating real-world phenomena where analytical solutions are hard to obtain.